280 million years after the Big Bang, a galaxy was already blazing. It should have been a faint knot of newborn stars. Instead, James Webb found MoM-z14, bright, compact, chemically strange, and surrounded by a population that our pre-Webb models barely predicted. That number is the entire mystery. The universe is 13.8 billion years old. MoM-z14 appears when the cosmic clock had completed only 2% of that time.
Its light has spent roughly 13.5 billion years crossing expanding space to reach us. And in January 2026, spectroscopy pushed it just beyond the previous record holder, JADES-GS-z14-0. One record does not break cosmology, but here's where the number becomes uncomfortable. The survey team estimated that bright galaxies at this distance are more than 100 times as common as pre-JWST consensus models expected. MoM-z14 is not a lone lottery winner. Webb keeps finding a universe that's switched on too quickly. The telescope sees this far because the expansion of space stretches ancient ultraviolet light into infrared. Webb separates that light into a spectrum, looking for a sharp break produced when neutral hydrogen absorbed shorter wavelengths. In MoM-z14, that break and several ultraviolet emission lines place the galaxy at redshift 14.44. This is not a fuzzy photometric candidate. It has a spectroscopic address. The object is also tiny. Its measured effective radius is about 74 parsecs, a few hundred light-years. Yet it is intrinsically luminous. Its recent star formation rate rose dramatically in only a few million years. The light is consistent with a young stellar population, not a giant active black hole doing all the work. And then there is the chemistry. MoM-z14 shows unusually strong nitrogen relative to carbon, a pattern also seen in some ancient stellar populations. Its immediate surroundings appear more ionized than standard reionization models expected at this time. Somehow, in a universe still filled with neutral hydrogen, this small galaxy had already built a local bubble and begun processing elements through stars. The previous record holder makes the same point from another angle. JADES-GS-z14-0 existed only 10 million years later. Follow-up observations detected oxygen around it, meaning massive stars had already formed, lived, exploded, and enriched the galaxy before the universe reached 300 million years old. The question is not whether the Big Bang happened. Independent evidence for an expanding 13.8 billion-year-old universe remains overwhelming. The question is how darkness became organized light this fast, and that's where the easy explanation begins to fail. When Webb's first deep fields arrived, several early galaxies looked almost as massive as the Milky Way. That would have been catastrophic. There had not been enough time for gravity to assemble enough dark matter, pull in enough gas, and convert that gas into hundreds of billions of stars. At first, that should sound like proof that the cosmological model is wrong. It is not. Webb measures light. Astronomers then infer how many stars produced it. A wrong assumption about those stars can turn a bright, lightweight galaxy into an imaginary heavyweight. The first major correction came from the little red dots, compact red sources that crowded Webb's early images. Some contain rapidly feeding black holes. Gas falling toward those black holes becomes intensely luminous, making the host galaxy appear to contain far more stars than it does. Remove those contaminated objects from the mass census, and the alleged galaxies that broke the universe fall back inside the broad limits of Lambda CDM. But that's not the end of the problem. The impossible masses softened. The impossible abundance remained. Webb still sees too many bright galaxies at redshifts above 10. They are not all giant. They are simply producing more ultraviolet light earlier than the old recipes generated. One answer changes the stars themselves. Astronomers usually convert light into mass using a stellar distribution measured nearby. Many small dim stars, fewer massive bright ones. The first galaxies formed from gas with almost no heavy elements. That gas cooled and fragmented differently,
allowing a top-heavy population with a larger share of massive stars. A galaxy built that way produces much more ultraviolet light for the same total mass. Another answer changes the rhythm. Early galaxies did not need to form stars steadily. Dense gas could collapse in violent bursts.
MoM-z14 appears to have increased its star formation by about a factor of 10 over its most recent 5 million years. Catch enough galaxies during brief flashes like that, and a survey finds a bright population without requiring impossible amounts of matter. A third answer is efficiency. In today's galaxies, feedback from young stars and supernovae heats gas and throws much of it back out. In the denser early universe, some halos converted gas into stars far more aggressively.
Studies of massive galaxies in the first billion years find no clean break with Lambda CDM, but the most extreme systems require an unusually large fraction of their available ordinary matter to become stars. Each correction protects cosmology by rewriting astrophysics. The dark matter framework survives. The recipes for dust, stellar masses, starbursts, and black hole light do the moving. And yet one result refuses to become ordinary. Even after the mass corrections, the universe still built luminous systems faster than pre-Webb forecasts. Models can match the counts by changing early dust, using top-heavy stars, and allowing burstier formation. But these changes are not cosmetic. They describe a first generation of galaxies unlike anything alive today. Then everything gets stranger, because Webb did not only find early galaxies that were bright, it found galaxies that already knew how to organize themselves.
In July 2026, researchers reported that spheroidal galaxies seen between roughly 400 and 900 million years after the Big Bang already followed a recognizable structural law. Larger systems had lower average surface brightness than smaller, denser ones, an early version of the Cormendy relation measured in mature elliptical galaxies. That should not sound dramatic. It is. The first billion years were expected to be dominated by clumps, mergers, unstable gas, and unfinished structures.
Yet hundreds of Webb images show that some young spheroids had already settled onto an organized relationship between size and brightness. They were more compact and brighter than nearby ellipticals, but they were not architectural chaos. Here's the real twist. The impossible galaxy story began as a mass crisis. It has become a timing crisis. The universe had to make dark matter halos, funnel gas inward, ignite extreme star formation, enrich that gas with oxygen and nitrogen, grow black holes, clear ionized bubbles, and establish repeatable galactic structure, all before the cosmic clock reached 1 billion years. Lambda CDM does not specify every detail of that process. It supplies the expanding universe, cold dark matter, and the initial scaffolding. The baryonic machinery inside the halos is messier. Gas cooling, turbulence, radiation, stellar feedback, dust, mergers, and black hole growth. Webb is revealing that this machinery ran in a mode our older simulations did not capture well. The model survives, but it has to work for it. There is still a path to new cosmology. If future spectroscopy confirms a large population whose masses and abundance remain impossible after black hole light, stellar populations, dust, and survey biases are removed, then the underlying dark matter framework faces a deeper problem. That threshold has not been crossed.
Current observations demand radical early astrophysics before they demand a new universe. That verdict is less sensational than Webb disproved the Big Bang, and far more interesting. The telescope did not find galaxies older than the universe. It found a universe capable of building stars and structure with terrifying speed. Return to MoM-z14. It is not an old adult galaxy misplaced in a nursery.
It is a young object, living at an intensity the modern universe rarely reproduces. Compact, rapidly brightening, chemically enriched, and visible across almost all of cosmic history. Its existence is allowed. Its abundance is the warning. Before Webb, simulations told us the first few 100 million years should be dim and sparse. Webb looked directly into that darkness.
and found factories.
Every new record has pushed the same message closer to the Big Bang. First, JADES-GS-z14-0 at 290 million years, then MoM-z14 at 280 million, and behind them, an entire population waiting to be counted. We know the universe is not twice as old as we thought. We know the most dramatic early mass estimates were inflated. And still, the first galaxies arrived brighter, faster, and more organized than expected. James Webb did not break cosmology. It broke our timeline for how quickly the universe could become complicated. Next, Webb may have detected a chemical signature of life 124 light-years away. The signal is real. The conclusion is not.